In this video, we're going to take a look at confidence intervals. They are going to be one of two remaining topics that we have for the rest of the semester. So we're going to look at a number of different types of confidence intervals, again, which I will be talking about shortly. And that'll be here in Chapter 8. And then starting in Chapter 9 and continuing into Chapter 11, we will be talking about hypothesis tests, which is the one other major topic that we'll be looking at. Both of them rely really heavily on having a solid understanding of the sampling distributions that we talked about back in Chapter 7. So hopefully you have a decent grasp of that, and if you do, most of this will make a fair bit of sense, hopefully. Okay, so let's start talking about confidence intervals. A confidence interval is used to try to predict some feature of a population. And we are trying to predict that feature of the population based on some sample that's taken. So a confidence interval is meant to predict some feature of a population. Based on a sample that's been taken. And so if we look at what I've got written up here, we're in this case going to be talking about a confidence interval for a mean. So the feature that I'm talking about, the feature that we're trying to predict of the population is going to be the mean. We want to predict the mean of a population, the average value in a population based on some sample that's been taken. And in this case, we're going to assume that sigma, which is the population standard deviation, that it's known ahead of time. And I'll talk a little bit about why this isn't necessarily a realistic assumption, but in subsequent sections, we'll have workarounds that allow us to relax this criteria. But for now, the easiest way to kind of get a foundational understanding of what a confidence interval is for this type of a problem. So, confidence intervals are actually things that show up all the time. You've probably dealt with one or read about one without even realizing it. So in the lead up to elections, for example, they will often give polls that try to predict the proportion of voters that plan to vote for a certain candidate, or what is the proportion of voters that plan on voting in a given election. Those are confidence intervals where instead of trying to find the mean, we're trying to find the proportion of a population that falls into some category. And we'll actually talk about those subsequently in section 8.3. But the idea is when you hear about one of these polls, they conduct a poll and they try to predict some value. Let's say the percentage of people that plan to vote for a certain candidate. At the end of that, they'll always say this poll has a margin of error of plus or minus 3%, or plus or minus 4%, or plus or minus 2%. And that plus or minus is what makes up what we call the interval. That's what gives us our confidence interval. What they're saying is they took a poll and they think that's their best guess for the value, but they're really not sure. And so they're kind of creating a little window around that number. So if they think 45% of voters plan to vote for a certain candidate, but they say plus or minus 2%. Well, what they're really saying is 45% is our best guess, but the plus or minus 2% means it really could be anywhere from 43% up to 47%. And that all falls within the margin of error of the sample that they took. That is a confidence interval. So I'm going to talk about how we can come up with one of those confidence intervals with that little plus or minus margin of error. So let's say in this example, and I'm going to do this via example because I think this is the easiest way to do this. So let's say in this example, we want to find the average age of a US citizen. So we want to predict the average age of a US citizen. Instead of going out and conducting a poll where we look at the entire population, all 330 million US citizens, instead, we would probably just take a sample. So let's say that we took a sample of 100 people. So we conduct a simple random sample. I'll just shorten that to a random sample. But we took a good sample, so a simple random sample of 100 people, 100 US citizens. And let's say that that yields an average age of 38.57, hypothetically. So this is the number that we got for our sample mean. We have x bar equals 38.57, and we want mu. So let me give you a quick reminder of what these two symbols mean. X bar is the symbol that we reserve when we're talking about the average or the mean of a sample. So this is our sample mean. This is the average age of those 100 US citizens that were picked in our sample. We want mu, which is the average age of all US citizens, all 330 million people. And this is, again, the whole point of taking a sample. Whenever we take a sample to find some features of it, not because we are intrinsically interested in that particular set of 100 people, but instead because we're interested in the entire population and we want to try to generalize this number to this number. So let's think about it. What are the odds that this number, 38.57, is exactly correct, that it exactly matches the true average age of all US citizens? It's basically slim to none. So so is mu equal to 38.57? Not very likely. In fact, it's very unlikely. And so we say, okay, we found this number. I'm assuming that the true age is probably close to it, but it's definitely not exactly going to be that exact same number. But what if we start adding a little bit of our margin of error to it? So what if we start adding a little buffer to it? So the next question is, what if we add a plus or minus 1 year buffer? So in that case, we would be saying, is mu between what two ages? So plus or minus a year from this number. Well, if I subtract a year, I'd be at 37.57. And if I added a year, I'd be at 39.57. So the first question was, is mu exactly equal to 38.57? Probably not. Is mu between 37.57 and 39.57? So we've added and subtracted a year, created a little buffer around this. More likely, but still, I'm not very confident. Let's say maybe. But what if we do this? What if we add a plus or minus 10-year buffer? So the question that we're asking is, let's bullet point these, is mu between, so adding and subtracting 10 years from our original value gives us 28.57 and 48.57. And now that I've added plus or minus 10 years, I'm asking about the average age of a US citizen. Is it between about 28 years old and about 48 or 49 years old? Probably. I'm pretty sure now. And so what you can see is happening is hopefully two things. We are slowly making our margin of error bigger and bigger and bigger. And as we make it bigger and bigger and bigger, we become more and more confident that we're capturing the true value of mu somewhere in that range of values. So we've gone from guessing one specific number to guessing a pretty big range of numbers. And we went from being pretty sure that we were guessing our value incorrectly to the point that maybe yes, maybe no, all the way up to being probably. And if we really wanted to take this to the extreme, what if we add plus or minus, I don't know, just make it easy, go in factors of 10, 100-year buffer. Well, that's going to look even more interesting. This number, when I do minus 100 years, goes negative, and it goes way negative, like negative 62. So the question is mu between whatever. We can do this on a calculator real fast. Subtract 100 from that. It'll be what? Negative 61.43. Do that correctly, maybe. And adding 100 is 138.57. So now we're asking, is mu the average age of an American between negative 61 years old and 140 years old? And the answer is yes. I'm 100% sure. Right? We can't even have negative ages. The oldest person in recorded history only lived to be like 120 or something like that. So I'm 100% sure that the average age of a US citizen is somewhere between some negative number and 140 years old. I'm 100% sure. And so we've got this trade-off, as I was mentioning a minute ago. Two things are happening. We are making our buffer larger and larger and larger, and as we make that buffer, that margin of error larger and larger and larger, we become more and more confident that our interval captures the true value of mu. So we want our interval to capture the true value of mu, somewhere in that interval. Make this a little bigger. As we make the margin of error, oops, and let me use the correct terminology. As we make the, we're going to call this the margin of error. Let me underline this because this is going to be the term that gets used. The margin of error larger, we become more confident that our interval captures that true value. The terminology we'll use for this is that our confidence level can increase. So if we look at the example that we're talking about up here, we can actually kind of define these two terms that are going to be really important, the margin of error and a confidence level. There's going to be some other terms that are important. One other term that I want to mention is something called a point estimate. This number right up here, the value of x bar in our sample, our best guess. So we took our sample, we found the average age to be 38.57. we said in all likelihood that number's wrong, but it's still the best guess. If you could only guess one number, if you didn't have the ability to add a little margin of error, a little plus or minus buffer, this is the best number you could possibly guess based on the data available to you. So we call the number, in this case, x bar equals 38.57, the point estimate. The point estimate is the best possible guess if you only could guess one number. It's the best guess, given the available data. So I realize we're writing a lot here and we're introducing some terminology, but hopefully what we've been talking about so far is also relatively intuitive. We're trying to guess an interval. So ultimately our confidence interval is going to be a set of numbers like we've got here, where I've got two numbers, a lower bound and an upper bound. And what we're going to do is we're hoping that the true value of mu falls somewhere between those two numbers. And as I make the confidence interval larger and larger and larger, I become more and more confident that we're capturing the true value of mu. But also, if I make it so big, if I make it sufficiently large, I can be 100% sure that I'm getting the true value correct, but the interval becomes useless. So we have this sort of competing set of facts going on here. So let me just zoom back in here. We'll come back down in a minute. I'm wanting to figure out the average age of a US citizen. I can guess with a very high level of confidence that it's somewhere between, say, these two numbers. Or even here, pretty high level of confidence between 28.57 and 48.57. But that's still a 20-year span. We've made the interval so large as to not be useful anymore. So what if you can tell me that you're 100% sure the average age of a US citizen is somewhere between, 25 years old and 55 years old? That's not helpful. That's such a broad range that it doesn't actually narrow it down for us. That's just common sense. On the other hand, I can guess one single value. I think the average age of a US citizen is 38.57 years. On the other hand, so I've got an answer that's very specific, but I also have a very low level of confidence that I'm right, which makes that number also not terribly useful. So we want to find sort of a trade-off. We're looking for a small enough range that we've sufficiently zeroed in on the correct number. So we want our interval, we want essentially using the formal terminology that we've got down here, we want our margin of error to be small so that we're sufficiently zeroed in on the correct value. But at the same time, we also want our confidence level to be high. We don't want to make our margin of error so small that we have a 0% confidence that we're getting things correct. So this is kind of the trade-off that we're looking for. Let's go through and see if we can figure out how we can determine this. So oftentimes, so let me start this over. What we do is we pick a confidence level. So we will pick a high confidence level and then go through the math to make our margin of error as small as possible given that confidence level. Okay, so this is the idea. What we want to do is we want to say, I want to be 95% sure that my confidence interval is correct, or I want to be 90% sure, or I want to be 99% sure. We'll pick a confidence level. By default, the most common value that's used, and this is left off when you hear those polls on the news about 45% of voters planning to vote for a given candidate, what they don't tell you is typically by default, they're using a 95% confidence level. That is the default number. So a 95% confidence level is the default, more or less. But what that means is they're not 100% sure that they're getting their confidence interval correct. They're only 95% sure. So when you hear that 45% of voters plan on voting for a given candidate and the margin of error is plus or minus 2%, what they're saying when they leave out the fact that their confidence level is really only 95% is they think that between 43% and 47%, which is the 45 plus or minus the 2 that I mentioned, so 43 to 47% plan on voting for that candidate, but they're not even 100% sure of that. They're really only 95% sure that that range of values is correct. And so this is one of the things that you saw in the 2016 election, where a lot of the polls predicted that Hillary Clinton was going to win, but obviously Donald Trump wound up winning. And part of what was going on there is issues in the way that they were sampling their data, right? So if you don't take a good sample of your data, then you're not going to get good results. But part of it is even if they did take a good sample, the confidence interval is never 100%. If you're going to get it right 95% of the time, that still leaves a window of 5% of the time that you could get that answer wrong. And so just keep this type of thing in mind. Statistics are telling us the most likely outcome. They aren't guaranteeing an outcome. So in this case, a 95% confidence level is going to be what we're going to use. And we want to make the margin of error as small as possible. So let's actually try to do it for this problem. So let's zoom back out, remind ourselves what we're talking about. So this is the example, if I can get it all on the screen at once, maybe. Hopefully this is readable. We're trying to predict the average age of a US citizen. Our sample gave us 38.57. We know that that's probably wrong, so we need to add a buffer to it. And the goal is to find the smallest possible buffer that'll still allow us to be 95% sure that the true value of mu falls somewhere in the window. So we've got a couple of example windows that we've come up with, some that we're less sure are correct, some that we're more sure are correct, some that we're 100% sure are correct. But we want to make the smallest possible window that allows us to be 95% confident. So basically what we're going to do is formalize, using statistics, the process that we can go through to quantify sort of our level of certainty and quantify this margin of error. So how are we going to do this? What I want you to think back to is the central limit theorem, which was the big discussion that we talked about basically at the end of section 7.3 when we talked about sampling distributions. So to do this, so we wanted to, let me finish this sentence here. We'll pick a high confidence level and then try to minimize the margin of error. A 95% confidence level is the default. How small can we make the margin of error? So that's the question. And we are going to use math. We're going to use statistics to figure this out. So we need to start with the sampling distribution. Recall the central limit theorem, which I will write down here because you probably don't recall it. The central limit theorem basically says that if we take a large enough sample, and the cutoff for large enough is greater than 30, then the sampling distribution, so for a large sample, basically n greater than 30, the sampling distribution is approximately normal with the following. The mean of our sampling distribution, so mu x bar, is equal to mu. The mean of our sampling distribution matches the mean of the population, which is what we're trying to predict. This is the value we're trying to predict. And also, the standard deviation of our sampling distribution is equal to the standard deviation of the population divided by the square root of n. So this is what the central limit theorem tells us. It tells us that we're getting, when we take our sampling distribution, it's going to be approximately normal with these two statistics. We know what the mean of it is. We know what the standard deviation of it is. So in this case, what we're doing is we're saying visually the following is happening. And this is going to be a picture that we're going to draw a lot. So here is my normal distribution that is my sampling distribution. So this is my sampling distribution. It's a normal distribution with a random variable equal to x bar, right? X bar is the sample mean. We know that the true center of this curve is mu. That's literally what is stated in the central limit theorem. The center of our sampling distribution, the mean of all of our distribution of all the x bars, it's equal to mu. The question is, we found one particular x bar. So we took a sample. We took a sample of 100 individuals, and we found this particular x bar. X bar was 38.57. So we got one sample, and our x bar falls somewhere on here, but we don't know where. I don't know if that 38.57 that we found is above the true average. Maybe the true average age of an American is only like 35 years old, and so 38.57 is somewhere over here to the right of mu. It's a larger number. Maybe the true average age of a US citizen is more like 40, and the 38.57 that we found is below the true average value. I don't know exactly where our particular x bar fell, so this is the idea. I don't know if it fell over here. I don't know if it fell over here. I don't know if it fell over here, over here. Where is the x bar equals 38.57? We don't know. But I know that it's much more likely to have fallen close to mu than to fall far away from mu. That's the nature of the normal distribution, right? Most of the values of x bar will fall pretty close to mu, maybe a little bit above or a little bit below. And it's much less likely for an x bar value to have fallen really far away at one of these extreme outliers out here near the tail. Hopefully this makes some intuitive sense. So even though I don't know exactly where our x bar value fell, I don't need to be 100% sure. We are only wanting a confidence level of 95%. So if we want to be 95% sure, all I need to know is where are the most common 95% of places that x bar could fall. And that's going to be here. If I chop this curve off and I delete a little bit in here, and I write that this middle part is 95% of the area, then what it tells me is, even though I don't know exactly where x bar falls, I'm 95% sure that it falls between right here and right here, because this contains 95% of the most common values. So these two cutoff points on either side, symmetrically around the center, this is the 95% of most common values where x bar could fall. And that leaves us with only 5% out here in the tails that are sort of the unlikely regions for x bar to fall. So this is what we're saying. Even though we don't know where x bar falls, we're 95% sure it falls between the lines I've drawn above, which is in the middle 95% of the sampling distribution, right? Those are the most common values, the values close to mu. So all I need to do is figure out how big to make our margin of error so that as long as x bar falls somewhere in this range of values, in this most common 95% of values, the margin of error will make our range large enough to capture the true value of mu down here. So what I'm suggesting is, let's draw this picture again. Here's my picture. One more time. All the possible values of x bar. Here's the value we're trying to capture. And I'm saying, okay, here are my two cutoffs. This middle area is 95%. If I write it as a decimal, I'll write it as an area of 0.95. What I'm saying is that as long as x bar, so let's say x bar falls right here. Let's say hypothetically, our x bar, which was 38.57, let's say it falls right on the edge of this 95% of the most common values of mu. How large do I need to make my margin of error, my buffer, so that it captures the true value of mu? Well, what I'm saying is, okay, let's say this is where our value is. I need to add a buffer to it. So if I make my buffer look like this, it's not big enough because it's not reaching all the way over here to get the true value of mu. I need to reach all the way down to get to this point right here. Here's the true hypothetical middle value of mu. My buffer isn't big enough yet. So how big do I need to make it? Well, I have to have it reach all the way over to, boom, right there. And it has to be symmetric, right? We're always doing a plus or minus. So this distance right here is what we're going to call the margin of error. It's that plus or minus buffer. And what we're going to use is the letter m. So lowercase m is what we'll use for the margin of error. And what I'm suggesting is, if x bar fell right here, right on the edge of the 95% of most common values, I need to make the margin of error large enough that it'll reach all the way still over to the center of the graph, from the edge to the center, to still just barely capture the true value of mu. And the idea is, hypothetically, what we can think of is, let's see if I can get this to work the way I'm wanting it. No, this might not work. Let me do a couple of little erasures here and see if I can kind of demonstrate almost with a little animation what I'm trying to get at. So let me erase some of this stuff. Give ourselves a little bit of room. I guess I did need to erase that last part. Okay. So let me just, here is our little margin of error. Okay. Last of this. And actually, you know what, while we're at it, let me take that little x bar along for the ride as well. Okay. So imagine that this is our margin of error. And right now, I've got it sitting in a position where it's right, oh, come on now, why is it separating? Undo that, I want to take the whole thing. Okay, here we go. So right here, I have it sitting right at the edge where that dot in the center of my interval with the x bar over it is right at the edge of our interval. And as I start sliding it to the left, if it turns out that x bar is not all the way over here at the extreme value, so again, the point that I'm interested in is this dot right here. This is the dot that I want to keep track of, that I'm following. This is where x bar is. It sits right at that dot. So right now it's right at the edge of the 95% most common values, and we've made our margin of error just big enough that it's capturing the true value of mu, which is that line at the center of the curve. If it turns out that x bar is even less extreme, I can make x bar be over here, where it's an even more common value. You know, it's not at the extreme edge of that 95%. And my interval, you'll notice, still is wide enough to contain the true center value of mu. And as I shift it over here, we're doing the same thing. It's still containing the true value of mu, true value of mu, true value of mu, all the way till we get to right here. And it should be, if I'd drawn this more symmetrically, now I can cheat and come back and actually do this. This line needs to be right there. So this line was a little bit off. There we go. And so again, what I've got is basically this interval. As long as x bar, the center of this interval, falls somewhere between this line on this side and this line on this side, the interval will always contain the center of the curve. See, right now, the center of the curve is contained at the far left end of our confidence interval. And as I shift it over here, it goes to different points. And by the time that dot gets way over here to the other extreme side of the 95% of the most common values, now the center of the curve is contained at the far right side of the interval, right here, just barely capturing the true value of mu. And so as long as x bar falls somewhere in the most common 95% of values right here, my interval is going to capture the center of the curve. It's going to capture the true value of mu, as long as x bar stays between right here and right here. And so the only time that it won't capture the true value of mu is if our x bar were to suddenly go into one of these tails. So notice now our x bar value at the center of our curve is pointing up into the tail. It falls over here in the tail now. And when x bar falls in that tail, our interval is no longer large enough to capture the center of the curve over here, right? I'm not able to capture the center of the curve. This thing reaches toward it, but doesn't quite get there. But that's okay, because I don't want to be able to get this right 100% of the time. I only want, based on our 95% confidence interval, I only want to be correct 95% of the time. So whenever x bar falls out into one of these two tail regions, my interval won't reach and capture the true center. But that's fine, because how often will that happen? Well, that'll only happen 5% of the times, because that's the amount of area that's in these two tails. The other 95% of the time, it's going to fall somewhere in this center region between the two vertical lines that I've got. And as long as it does, my interval is big enough to capture the true value of mu. This is the idea behind a confidence interval. So hopefully this makes some sense. Let me kind of draw some of this stuff back. As long as this center of the curve falls between this point right here and this point right here, these two little arms will reach out enough to capture the center of the curve, which is the value of mu that we're trying to predict. And only when this center of this little interval falls into one of these two tail regions will the arms not be long enough. But how often is that going to happen? That only happens 5% of the time, because x bar only falls into these uncommon regions, these unlikely regions, 5% of the time. But again, this margin of error is this distance right here that we're going to call m. And so that's all I need to figure out. I just need to figure out the distance from the center of a curve out to the edge of the 95% of most common values. So the margin of error is the distance. And I put distance because it's a distance visually, but in terms of the actual units we're going to use, it's going to have units of whatever x bar is, in this case years, so age. But it's the distance, visually at least, from the center of the curve to the cutoff of the 95% of most common values. And again, if we change it to a 99% confidence interval, we'd change the 95 to a 99. Or if we only cared about a 90% confidence interval, we could change this number to 90%. Okay. Whew. So conceptually, that's what's going on. What is this distance? Well, one thing you might remember is this 95% is a number that we've seen before. We saw when we looked at the empirical rule back in when we were introducing the normal distribution, it was that 95, well, it was three different numbers. Within plus or minus 1 standard deviation of the center, 68% of the data fell. And within plus or minus 2 standard deviations from the center, 95% of the data fell. And so it turns out this distance is about 2 standard deviations. So if we recall the empirical rule, ,95% of the data falls within plus or minus 2 standard deviations. And it's about 2 standard deviations. In fact, we'll see in a minute that it's not going to be exactly 2. So, how do we figure out exactly what that distance is? Well, the easiest way to do it is using our old tables. So let me open and add a table in here. See if I can find the table that I'm looking for. Open this up. I'm going to actually put in 3 different pages of the table. Let's insert all of these pages. Okay. And of course it covered up our other work. So let me move these pages off to the side. So the first 2 pages are the ones that we've already looked at. These are the normal distribution, what we call the Z tables. We're also going to be using this table here, which is the one for something called a student's T distribution, which we will talk about shortly. But all of these tables will be useful. So what I want to do in this case is figure out how much exactly, so what exactly is the z-scores? We said it's close to plus or minus 2 standard deviations. I want to find the exact z-scores that bound the middle 95% of the data. And so to do that, so what are the exact z-scores? Bounding the middle 95% of data. Well, these are going to be called the critical values. Or critical value. And are given by we're going to denote them as a z with a little subscript of alpha over 2. This alpha is a Greek letter. It looks kind of like the little Jesus fish type shape. And for now, you just need to know that that's the symbol that we're using. It's a z with a subscript. So this alpha over 2 is kind of tiny and down bottom to the right, kind of like how we write exponents up and to the right. This is written down and to the right and tiny. This notation will make more sense when we get to chapter 9. We'll come back and discuss this again. But for now, all you need to know is this is the notation that we're using for these critical values. How do we find them? What we need to do is find the cutoff z-score that bounds the middle 95% of the area. But the way this table works is that it measures the area not for the middle part of the curve, but it measures it all the way from the left tail. So coming back to our picture, let's draw this curve yet again. I want to know on this, we've got our cutoffs. Here's our whatever middle 95% of the data. So 0.95. I want to figure out this z-score. But to use the table, I need to recall exactly what I just said. The area here isn't measured as the middle, so I can't just look up 0.95 as the middle area. I need to find the area all the way into the left tail. So if I have 95% of the area in the middle, that leaves an area of 0.05, the last 5%, for the two tails. But because it's symmetric, that 5% is split up evenly between the two tails. So just this area over here is going to be 0.025. It's half of this 0.05. And then the other half is this area over here. This is the other 0.025. And again, the middle area has, we just said, 0.95, 95% of the area. So if I want this z-score here, and I'm measuring everything to the left, because that's how our table works, I need to figure out what is this combined area of everything to the left. Well, it's not just the 95% in the middle, it's also this extra 2.5% in the tail. And so this combined area up to the z-score that we're interested in is 0.95 plus the 0.025, which gives me 0.975. This is the area that I need to look up in the table in order to find a z-score. So we're basically going to be using our table in reverse. Remember, the numbers in the middle are areas, and the z-scores are along the edges. So in this case, I need to find the number in the middle, the area, as close as possible to 0.975. So find area as close to 0.975 as possible. And again, that 0.975 came because we're not looking at the middle 95%. Instead, we need to take into account the left tail, and that means a combined area of 0.975. So if we go through this, I see some 0.97s down here. This is still a little high. Let's see, right there, 0.9750. It shows up almost exactly here. So there's the value that we're looking for. That's the area that we needed. Oops, not throw this around here. And what is the corresponding z-score? It is, come on now, it is 1.96. So the z sub alpha over 2, this z-score right here is 1.96. It's not quite 2, it's 1.96. That is the one that corresponds to the middle 95% of the area. Now that we've found this number, it turns out whenever you're dealing with a confidence interval of 95%, you're always going to have this exact same picture. We're always going to be interested in the middle 95% of our normal distribution. And this z-score that cuts off that boundary is always going to be 1.96. I'm also going to show you how to use now a faster way using this table A3 that we haven't used yet. If you look at this table, it works differently. The numbers in here aren't areas anymore. The numbers in here are z-scores. And degrees of freedom is something we will discuss later on. We don't need that right now. But what I do want to look at is right now at the bottom here where it says confidence level. we are going to be using these common confidence levels a lot. So instead of having to draw out the picture like we did over here, where we find the middle area here, and then we add in an additional area in the tail by figuring out how much leftover area is there and taking half of that, and finding this number, and then looking it up in the table to get the z-score we're interested in. Most of the time, we're going to be able to just jump to this. And what we're going to do is come down to the bottom. Right now, all we care about is this bottom row labeled Z, because we're dealing with z-scores. And if we're interested in a 95% confidence level, what is the critical value? Boom, right above it, 1.960, the exact number that we just found. If instead they were asking for a 99% confidence level, so let me zoom in more so you can see it even better. A 99% confidence level, boom, there's our critical value. This is the z-score that bounds the middle 99% of area, 2.576. If I only wanted a 90% confidence level, here's the critical value, z-score, that I need, 1.645. So this is going to be probably the first place you should check, and only if the confidence level that's specified doesn't show up in this table down here at the bottom should you resort to finding it the way that we just did here, where you have to kind of draw the picture, figure out the combined area of both the center region plus the left tail, then look up that area in the meat of this table and back out what the corresponding z-score is. But that is the critical value. So what we found so far in all of this is we found that our margin of error is 1.96 standard deviations wide. Our margin of error is 1.96 standard deviations wide. But that's not quite useful yet. So what we've basically said is this is how big I need to make my buffer, 1.96 standard deviations. But it doesn't help to say, I think the average age of a US citizen, which is thinking back to the way we started with this, that's the problem we're trying to solve. I think the average age of a US citizen is 38.57 years, plus or minus 1.96 standard deviations. Well, what does that mean? What is a standard deviation? I don't want an answer to be plus or minus standard deviations. I want it to be plus or minus years, just like the results that we had up here. I want to give us plus or minus a number of years, not plus or minus standard deviations. So we need to convert the number of standard deviations into years. And to do that, we need to know how big is a standard deviation, because standard deviations will be measured in years. So how big is a standard deviation? Well, remember, according to our central limit theorem, this is what we're trying to find. We're trying to find the sigma x bar, and it's going to be sigma over the square root of n. That means we need sigma to be specified. So we want sigma x bar, which is equal to sigma over the square root of n. We already have n. N is our sample size. Oops, but we need, so n is sample size. If I can stop hitting my erase button here. Sample size, and it's equal to 100 in this case, right? We said back at the beginning framing of this problem that we took a sample of 100 people to get that 38.57. And this is the population standard deviation. We need that value. Notice that it's not given in the problem yet, but if we come way back up to the beginning of the lecture, we were assuming that sigma had to be known. So this is kind of the weird thing. In all of these problems in this section, sigma will be given. Let's say that sigma is 20 years. The standard deviation of the age of US citizens is 20 years. Why is it weird that we would know this value, sigma? Well, if you think about the formula for standard deviation, so this is going to be a side note that I'll erase in just a minute, so you don't need to write this down, but recall, If you're trying to find sigma way back in chapter 3, we had a formula for the standard deviation, and it looked like this. We had to take the square root of the variance, and the variance was basically the sum of, we did x minus mu squared over n, or sample size. Looked like this. If I want to figure out what sigma is, I need to know all the information that's being plugged into here. What information is being plugged in? Well, I need to know the size of the population, n. I need to know all the individual ages of everybody. And I need to know mu. I need to already know the mean of the ages of the population. But mu is the thing that we're trying to predict. So this is what I meant when I said earlier that it's kind of weird and counterintuitive that we would somehow know sigma. If we want to know what sigma is, to compute sigma, we need to already know what mu is. And if we already knew what mu is, we wouldn't have had to do any of this problem. The whole point was trying to figure out what is mu. Right? We want to predict the average age of a US citizen. We want to figure out what mu is. If I already knew what mu was, which we need to figure out what sigma is, then this problem would already be done. So this is why it's kind of backwards, that we somehow know sigma without knowing mu. So let me just put, all that matters is it's weird to know sigma without already knowing mu. And so this isn't necessarily a realistic scenario. But what we'll see in the next section is we'll be able to relax this requirement, and we'll find a way to do problems where we don't know sigma, and those are going to be much more realistic scenarios. So we'll see that in the next video. Okay, so again, let's say sigma is 20 years, and let's just say that maybe it's because, we studied Canada. They'd already done their study, and we said the demographics of the US are similar to Canada. Their standard deviation was 20 years. Let's just use that for our standard deviation as well. Okay, so if I know what the population standard deviation is, then I can figure out what our sigma x bar is, which is exactly what we need. I've figured out that my margin of error, the distance from the center of my curve out to the edge of the 95% most common values, I know that this distance is 1.96 standard deviations. How big is one standard deviation? Well, let's figure it out right here. I need to know what sigma x bar is. So that means that sigma x bar, let me zoom back in so we can see, is equal to sigma over the square root of n, which is going to be 20 divided by the square root of 100, because n was 100. Square root of 100 is 10, so 20 over 10 is just going to be 2 when this is all said and done. So our sampling distribution has a standard deviation, sigma x bar, of 2 years. And our margin of error needs to be 1.96 standard deviations. The margin of error, m, is 1.96 standard deviations. So it's m equals 1.96 times the 2 years. And if we do that, we get about 3.92 years. That is the plus or minus that we need. This means, now that we've found our margin of error, that our confidence interval is that we think the true value of mu is 38.57 plus or minus 3.92 years. And so the actual interval, if we write out the lower bound and the upper bound, what we would say is we are 95% confident that, I don't know why I put a comma there, confident that the average age of a US citizen is between, so if I do my subtraction first, 38.57 minus 3.92, I get 34.65. And if I add 3.92, I get 42.49. 42.49 years. This sentence summarizes our findings. We are 95% confident that the true average age of a U.S. citizen is between 34.65 and 42.49 years. That's the 38.57 plus or minus the 3.92. I added and subtracted this number from this number to get these two numbers, our lower bound and our upper bound. So this is the idea. And again, a higher confidence level, if I want to be more certain that I'm getting the value correct, what that's going to require is in our picture, if I want to change it to a 99%, I'm going to need to move these boundaries out until they contain 99% of the area. What would that do to our margin of error? If these boundaries are moving out, my margin of error is always the distance from that boundary to the center. They're going to have to get larger. So if you want to be more confident that you're getting the answer right, you're going to have to make your buffer bigger. Your margin of error has to grow. If we're willing to be less certain, we can make this smaller. So if I only want to be 90% sure, I could get away with something smaller than this. The one other thing that's going to be important is really the only thing we have control over in all of this is n, our sample size. If you're the one conducting a study, you can choose how many people to sample. So sigma, that's just a feature of the population. We can't control that. But this number here is the n, the sample size, is going to affect our size of our standard deviation. That size of that standard deviation will in turn affect our margin of error. And so we'll see that in just a little bit. Okay, so let's take a quick breather here and just summarize what we've done, because this was a very long process. Look how much work we did to answer this question, right? Zooming all the way out. There is all of our work from the framing of the question that you can't read down to our answer. That seems like a lot of work, and it is. But the reality is we don't need to do that much work for every one of these problems. We can actually break this down. Now that we've kind of done this once and we understand what goes into it, I want to streamline this process for us because it's not nearly as bad as it looks. So we can summarize this whole thing into a 5-step process. And it's pretty easy. So I'm going to write these 5 steps. Step number 1, we need the point estimate. So find the point estimate. In this case, the point estimate is x bar, and it's given in the problem. So step 1 is, can you read the problem, basically? Step number 2, what we need is to find what we were calling the critical value. And that is the z-score, z sub alpha over 2, corresponding to the given confidence level. Right, so in this case, it was specified we were interested in 95% confidence. We know right off the bat it's going to be 1.96. If we said 98 or 99 or 90, just 90 instead, we could go to that table and look up those values. So corresponding to the confidence level. Step number 3, we need to find the standard deviation of our sampling distribution, that's sigma x bar. The word that we had for that sigma x bar was the standard error. So find the, standard error. Sorry about that. Find the standard error. which is our sigma x bar value, and it's just equal to sigma over the square root of n. In all of these problems, sigma will have to be specified somewhere in the problem, right? That was the whole idea here, is that sigma is known for all of these problems, and n will also be given, the sample size. Both of these numbers will be given. The fourth part is where we find the margin of error. If I can write margin of error, which is m, and it's equal to how many standard deviations times how big is a standard deviation. So it's going to be z sub alpha over 2 times sigma over the square root of n. So basically, all you do in this fourth step is take step 2 and multiply it by step 3. And that gives you how big the margin of error is. And lastly, once we have the margin of error, we construct the confidence interval. And the confidence interval is simply going to be x bar plus or minus m. So basically, we take x bar, which is the value we found in step 1, and we add and subtract m to it. M is the value we found in step 4. So this one is just step 1 plus or minus step 4. And that's our result. That is the entire confidence interval boiled down in this problem. So if we were trying to do the same problem that we just did quickly, so if we just redo the same problem. All we would do in step 1 is note that x bar is 38.57. That's given in the problem. Step number 2, 95% confidence level, if I can write again, 95% confidence level is going to imply that our z-score, our critical value, z sub alpha over 2, is, again, we just come over to this table, say, what's the confidence level that we're interested in? Oh, 95%, boom, 1.96, done. So we go look in our table and we find 1.96. Step number 3, we need to find our sigma x bar, and it's simply what we did a minute ago, right? It's sigma over the square root of n. Sigma would have been given in the problem. It was 20 over the square root of 100, and this is where we got 2 a minute ago. Step number 4, the margin of error is simply 1.96, the result of step 2, times 2, the result of step 3, 3.92. And the last step, 5, for our confidence interval, we get x bar plus or minus m. So that's going to give us 38.57 plus or minus 3.92. And we can write this in a couple of ways. We can write it the way that we just did. Another way you'll see it written is with actually writing out those values. We said it was 34.65 if I do the subtraction, less than or equal to mu, less than or equal to, what was it, 42.49. So I could write it this way. This is the same information. I'm saying I'm 95% confident that mu is between 34.65 and 42.49. These are the values, again, that I get when I add and subtract 3.92 from 38.57. Or you may also see it written in interval notation, which is just uses parentheses and writes it like this, 34.65, comma, 42.49. I believe this is going to be the form that most of your homework problems will require. It will require you to actually evaluate the addition and the subtraction and enter in the two values that mu has to fall in between. But that's it. That's how you can do one of these problems by hand that quickly. Once you have the process down, it goes quickly. And in fact, this same 5-step process is what we'll use for all the confidence intervals that we'll do in the subsequent sections as well. It'll be very, 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 very similar. while we're at it, let me show you how to do this on the calculator. So let's see here. So for this type of a problem, what we're going to be doing is clicking some buttons that we haven't clicked before. I want to go into the stats section, and I want to go into tests. So I'm going to click over to the tests, and this is going to be the option we're going to be using for all the remaining sections this semester. So stat tests. And what I want to do is an interval. You'll notice a bunch of these have Z's in them, some have T's in them, some have this word test. All these ones with the word test, those are going to be hypothesis tests, which again, that's what we're going to be doing in chapters 9 and 11. For now, I'm interested only in intervals, confidence intervals. So I need to look for the word interval or the letters INT. And this one right here, we're using z-scores, we're doing intervals. Z-interval is the option that I'm interested in. So I'll select that Z-interval. It allows you to do it from a set of data or from pre-computed statistics. So on the homework, if it just gave you the raw data, you would enter the raw data into a list by editing your list in the stats. But for us, I want to use pre-computed stats. We've already got the values that we need. So I'm going to assume we're already dealing with statistics because all those statistics were already computed for us over here. So now, if I come down here, it'll ask for sigma. That was the standard deviation of the population. That's going to be this number 20. So I would enter 20. For x bar, that is going to be our point estimate. That's 38.57. 38.57. It'll ask for n, our sample size. That was the 100. There were 100 people in our sample. And it asks for the confidence level. In our case, we're going to leave it as 0.95. I believe you can also enter it as 95 without the decimal, but I will just stick to the default notation here, 0.95, because we want a 95% confidence level. And if we hit calculate, what it will do is do all the computations for us, and sure enough, it'll spit out something that looks exactly like what I have written right down here, 34.65, comma, 42.49. It gives us the final answer that we're looking for right here. So this is how you can do this on the graphing calculator. As for dealing with this type of a problem in Excel, there's not really a good viable way, certainly not one that will translate to the spreadsheet in the lockdown browser for exams. So I'm not even going to bother with that. On exams, I will ask you to write out all 5 of these steps anyway. So even if you are good at doing this on the calculator and you can get the answer just that quickly, it's not going to be enough to get you the credit that you need. I'm going to make you go through all the steps anyways. So practice doing these by hand, kind of going through all the steps piece by piece. And if you have a calculator, you can always feel free to check your work on the calculator, but I'm going to force you to go through these steps anyways. So one approach is doing it by hand using the table. That will work for everybody. And if you happen to have a calculator, you can at least check your answer, but it's not going to actually help you get all the work you need that I'm going to require on the exams anyways. So there's no approach for Excel. There is an approach that everybody can use using the tables where we get this value and then just going through each of these pieces by hand. And you can also do it on the calculator. There is one other type of problem that comes up in these sections that I think is a useful one to talk about. So let me go back to maximizing this, and let's look at one last type of problem. This problem is called a necessary sample size problem. And this is actually a pretty realistic type of problem that shows up in these situations. So necessary sample size. And the idea is, in this case, more often than not, instead of just randomly doing an experiment, picking a sample size, and finding out what the margin of error is, much more common thing in scientific studies is to pick ahead of time what you want the margin of error to be. So figure out what you want basically step 4 to look like, how big we want this number. Right now it's plus or minus almost 4 years. That's not that narrowed down, right? This isn't that narrowed down, telling us the average age of a US citizen is between basically like 35 and 43 years old. That's a pretty big window still. So maybe we want to narrow it down to be within plus or minus 1 year or plus or minus 6 months. How can we do that? Well, the only thing we're going to have control over is how big of a sample size we take. So in a necessary sample size problem, we often want to pick the necessary sample size to yield or give a particular margin of error. Right, so we want to figure out ahead of time how zeroed in on the correct answer we want to be. And then from there, decide how big of a sample we need to do that. And this goes back to the other idea that we talked about. Again, bigger samples are better. If you take a bigger sample, you can get more zeroed in on the correct value that you're looking for. So let's say, in this case, we want to know the average shoe size. So as an example, we want the average shoe size of, let's say, American males within half a size. If I tell you, it turns out the standard deviation of shoe sizes of US males is 1.8 sizes. What is the necessary sample size for a, and let's pick a different number instead of 95%, just so we can get a practice using this. Let's say for a 99% confidence level. Okay, so I mentioned basically what we're talking about here is the step 4. Step 4 is the step, if we come up to the general version, where we compute the margin of error according to this formula. So this is the formula that we need to start with. We know that the margin of error m is equal to the critical value z sub alpha over 2 times sigma over the square root of n. And what I'm suggesting is we're trying to solve for n in this case. I'm going to have the problem framed so that we have figured out what the margin of error m is. In this case, we want our margin of error to be within half a size, so m is 0.5. We'll have the critical value z sub alpha over 2. We'll find that on the table in just a minute, but that's easy. We know we have a 99% confidence level, so that's all we need to find this. And we know what sigma is. The standard deviation of shoe sizes of US males is 1.8. So I have this value, and this value, and our goal is to solve for n. So right now, n is in the denominator, and it's being square rooted. If I want to solve for n, I need to get it out of the denominator. So what I would do is I'm going to just do some generic algebra on this formula to solve it for n. So I'm going to multiply both sides by the square root of n. So I'm going to have m times the square root of n is equal to z sub alpha over 2 times sigma. So all I've done is multiply both sides by the square root of n, and it canceled on this side, and we have the square root of n right there on this side. Then, to get n by itself, I need to divide out by that m that's sitting there. So I'm going to divide both sides by m, and that'll leave me with just the square root of n on this side. And on the other side, I'll have z sub alpha over 2 times sigma, the whole thing over m. And the last thing I need to do is undo the square root. Right now, n is being square rooted. If I want to get rid of that square root, I have to square both sides. Square is the opposite of square root, and that's what will undo the square root. So I just need to, there we go, square both sides. And I'll get z sub alpha over 2 times sigma over m squared. This is the formula that we can use for necessary sample size. And for us, we just need to plug in the values. We know that m is equal to 1/2, or 0.5. We know that sigma is given in the problem is 1.8. So both of these were given in the framing of the problem, right? 1/2 was our margin of error that we wanted, 1/2 a shoe size. Sigma, the standard deviation of shoe size, is 1.8. And the last one we need is z sub alpha over 2. It tells us that we want to use a 99% confidence level. So all I need to do is go back up and check the table. It's up here somewhere. Here it is. Again, we're looking at table A3. Table A3. And at the bottom of table A3, it has the various confidence levels. In this case, we want a 99% confidence level. So what is the corresponding critical value? The number right about above it, 2.576. So I'll come back down here, and we will use 2.576. So there are the values. I'm just going to plug those all into this formula, and then we can do it on the calculator. Here, let me move it over to the side. We'll get the calculator out. Let me turn it on and clear it. And we're just going to plug these values in. And we can even do it in the same format as all of this. I can start with parentheses. So I'm going to do parentheses. Z sub alpha over 2 was 2.576. 2.576. I'm multiplying that by sigma, which was 1.8. I'm dividing that by m, which was 1/2, so 0.5. Close my parentheses, so I have z sub alpha over 2 times sigma divided by m. The last thing I need to do is square the whole thing. The square button is right here, or you can do the up caret number 2. So I could either do that to get the square, or if I delete that, I can also similarly delete that. I can also just hit this button here, and it'll square the whole thing. And if I hit enter, it gives me 85 point, let's see what that number is, 85 point, boy, 9996, dot, 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 dot. Keep in mind, this is a sample size. You can't sample 85.9996 men to figure out what their shoe sizes are. You can only sample whole numbers. So this answer must be whole. And furthermore, and we must round up, always up. So in this case, that's not a problem. So we require, in this case, n equals 86 men. We need to sample 86 men to figure out their shoe size. But in this case, we're rounding up automatically because this number is one we would round up anyways. But even if this number was small, what if hypothetically we'd gotten 85.1? Why do I need to round up in that case? Well, the idea is that n is the smallest sample that we can take to ensure that our margin of error is of the required size that we're looking for, in this case to be 0.5. If I rounded down, so if it required 85.1 men, but I rounded down to 85, the idea is that we wouldn't quite be able to satisfy the margin of error of 1/2 that we were looking for. We'd be really close, but we couldn't quite get what we were promising. And this is kind of the general idea of these problems. We don't want to overpromise and underdeliver, so to speak. So It's fine if we use 86 min, even though that's a little bit more than we would need. It's going to ensure that our margin of error is a half or smaller, that we have zeroed in sufficiently. If I only used 85, it would have mean that we'd be really close to a half, but we hadn't quite zeroed in sufficiently. So it's okay if you can basically zero it into, 0.49 sizes. So instead of 0.5 or a half, if you could get it down to be within 0.49 sizes, it's fine to say, yes, I can get this within half a shoe size, even if we can do better than half a shoe size. But it's not okay to say I can get it within half a shoe size if we're not quite getting there. If I can only get it to be within 0.51 shoe sizes, it's not okay to say I can get it within half a shoe size. But if I can get it within 0.49, then it is okay to say I can get it within half a shoe size. And that's what rounding up versus rounding down does. Rounding up always ensures that we're going to be getting even better results than we're necessarily promising. Whereas if we rounded down, it would mean that we're not actually quite getting quite as strong of results as what we're claiming, or quite as narrowed in of results as what we're claiming. So this is the reason that we will always have to round up on these necessary sample size problems, even when it's a number that we would normally round down. So even this would round up. So even if we'd wound up with a number like this instead, we would still need to round up to 86. So keep that in mind. These necessary sample size problems, you've got to have a whole number for it to make sense, and we've always got to round up whatever decimal value that we wind up with. And again, this is how you would do it on the calculator, and this is the formula, or on any calculator rather, and this is the formula that we're using. So hopefully these all kind of make sense. This picture is obviously a lot to absorb, but the good news is once you kind of start to get this down and practice it, they become much, much easier. And the confidence intervals that we're going to do in the subsequent sections are going to wind up, I'll go through them and talk about them, but they're going to wind up following this exact same 5-step procedure with just very minor tweaks to what the formulas look like. But it's going to be the same 5 conceptual steps for all of the confidence intervals that we're going to do.